Salam sejahtera. Today we will continue our topic in 5.2 simple gas turbine for the ideal Brayton cycle. And as we know, for Brayton cycle, we use air as a substance, therefore we have to use formula hijau. So we revisit our topic in formula hijau we already discussed in previous lecture. So PV to the power of K is equal constant comes from polytropic equation. PV to the power of N is equal to constant. If N is equal to K, what is K? K is Cp over Cv. Sometimes we use K as a gamma. Alright, so if N is equal to K, then this equation will be PV to the power of K is equal constant, and this formula we call it as a adiabatic process. So this is adiabatic process and this is ideal gas equation. Rearrange this formula, we get P is equal to RT over specific volume. Then we replace P with this formula. So P RT over specific volume multiply with specific volume to the power of K is equal constant. Then this equation will give us TV K minus 1 is equal constant. Alright, and for process 1, 2, which is in a compressor, isentropic compression in a compressor, then we will rewrite this formula as a T1 V1 to the power of K minus 1 is equal to T2 V2 to the power of K minus 1, which leads to the T2 over T1 is equal to V1 over V2 to the power of K minus 1. And if we replace V is equal to RT over P in this equation, okay, then we will get T2 over T1 is equal to P2 over P1 to the power of K minus 1 over K. Okay, now we go to the PV and TS diagram. For process 1 to 2, 1 to 2, this is isentropic compression. Alright, and we know P2 is equal to P3 and P4 is equal to P1. And from formula hijau, we get T2 over T1 is equal to P2 over P1 to the power of K minus 1 over K. And this is equal to T3 over T4 is equal to P3 over P4 to the power of K minus 1 over K. Okay, now we go to the new terms from pressure ratio. So pressure ratio is RP. RP means the ratio of the pressure at the exit P2 over P1. Okay, so P2 is also equal to P3 over P4. Right. Then this equation, okay, we can simplify with T2 is equal to T1, then P2 over P1 we replace with RP. Okay, to the power of K minus 1 over K. And similarly with this equation, T3 is equal to T4 and P3 over P4 we replace with pressure ratio. And we will get Rp to the power of K minus 1 over K. Next, we go to the definition of backwork ratio. What is backwork ratio? Backwork ratio is the fraction of turbine work used to drive compressor. Okay, so the power that has been produced by the turbine, some of it used to drive compressor. So if someone asks you what is the back work ratio, this is your answer. Okay, and in formula, okay, back work ratio, or some books they write it as a R W R. WR means work ratio. All right, work ratio. WB, back, BW, if I'm not mistaken, sorry, BWR, BW, back work ratio. Okay, then back work ratio is the ratio between work of compressor over work of turbine. Okay, so work of compressor is H2 minus H1. Then we can write it also in CP T2 minus T1 over work of turbine, and from TS diagram or PV diagram, work of turbine is H3 minus H4 and equal to CP T3 minus T4. And back work ratio is important for you to remember. Okay, K. What is K? K is specific heat ratio, and this topic we already covered in chapter 3. Okay, and in this topic, we consider that K is constant throughout for air. Alright, the thermal efficiency depends totally on a pressure ratio. The highest temperature is the cycle at the end of combustion process. Okay, T3. It is only limited by metallurgical limits of the blade materials, and from this graph we can see that the greater pressure ratio, the 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 thermal efficiency will increase. And typical pressure ratio for gas turbine engine is between 5 to 20. Okay, so this is the blade for the turbine. Okay, and this is example of blade damage. Okay, and we already cover this topic in the Carnot cycle. Why in turbine we cannot allow the mixture, okay, the liquid in mixture enter the turbine, because it will cause the blade to damage and corrosion. Okay, all right, so that's all. Thank you.